Okay, let's get started. Okay, let's see what we covered in our last lecture. Uh, Wait, yeah, okay, I didn't update it here. Okay, so yeah, in our last lecture, we finished talking about the asymptotic equipartition property, and then we start talking about the data compression, right? Okay, and so for the AEP, we have the following four important. For the AEP, we have the following four important properties, right? So the first one, so it basically means that the value between the self-information and n times the entropy would be less than or equal to n times epsilon, right? So this is almost trivial, right? So that's from the definition of AEP, right? And then for the second property, so we know the probability that any element in the typical set is bigger than or equal is bigger than 1 minus epsilon, right? So basically, when n is sufficiently large, right? So it basically means that, so if we randomly generate a sequence, so with very high probability, that will be in a typical set, okay? So remember here, the important assumption here is that we consider a memoryless, discrete memoryless source, okay? So if that's not the case, then we need to do something else, okay? And then we see the cardinality of the typical set is pretty much given by 2 to the power of n times n hx, okay? So here's upper bound, here's the lower bound, but we can sort of ignore epsilon, right? Epsilon is very close to 0, then it's pretty much the same, right? Upper bound, lower bound are almost the same, okay? So that's the cardinality of the typical set, right? And the probability of each element will happen, roughly speaking, that will be 2 to the power of minus n times h, right? And so they're always almost equal probability, right? That's why it's called equipartition property, okay? So yeah, that's very important here. And then we start talking about the data compression, right? For data compression or source coding, so again, so we consider a DMS source, discrete memoryless source, right? And later on, so we're gonna assume we're gonna remove the memoryless condition. So we consider the source with memory, and we're gonna see how we're gonna deal with that, okay? And so in this class, so in like 90% of the 95% of this class, we consider the point-to-point scenario, right? So here is for compression, and later on we're going to talk about communication or something else. So we mainly focus on point-to-point system. Basically means that we have one transmitter and we have one receiver, something like that, right? So here for the compression problem, so we have an encoder here, right? After encoder, we use a letter M to represent the source information, right? And when the decoder sees M, it will have the estimated source information, which is x hat, okay? So that's the setting. And here is the detailed definition of this, right? So we define a source alphabet, we define the code alphabet, right? And so we say this code, right? 2 power of nr is basically the cardinality of the code, okay? How many elements are there in the code, right? Or the cardinality of this M, okay, of this M, right? And so encoding function is nothing but a map, right, from our encoding function to the code alphabet, right, from the source alphabet to the code alphabet, right? And here clearly we can see that if the cardinality of I is less than the cardinality of the source alphabet, and then we're going to have error, okay? And clearly, so what we want is the size of the cardinality of the code alphabet is less than the cardinality of the source alphabet. Otherwise, we don't have compression, right? All right, and then we can define the decoding function, right, which is the map from the code alphabet to the original source alphabet, right? And the probability error means that it's a probability when the source and the decoded information, they're not equal, right? And then we have our error probability here, and the rate of the code is given by this formula, right? So basically, it means that how many number of bits we need to represent the source information or to encode the source information, okay? So, and then we say the R is said to be achievable if there's a sequence of codes such that, so the error will become 0 when n goes to infinity, right? So here, remember, be careful here. So what we do here is that we construct a sequence of code, okay? And for each kind of encoder-decoder is a function of n, okay? And for each n, so we have an error probability. So as n goes to infinity, then the error probability will go to 0, okay? So we define a lot of like encoder and decoders here. Yeah, we define R star as the infimum of all the achievable R's, okay? So here we need to be more careful about the infimum. It's not the minimum, right? The difference between minimum and infimum is that, so infimum may not be achievable for finite n, right? There always difference is always an epsilon, okay? So it basically means that as long we can show that R plus epsilon is achievable, then we say it's achievable, okay? Very good. All right, so this is the first Shannon's first coding theorem, or the lossless source coding theorem. So this theorem tells you that, okay, for a DMS source, okay, the R star will be given by entropy. Okay, so basically, so it's very meaningful, right? Because it tells you that the entropy is the minimum code rate you can expect for, right? So the meaning of that, okay, is like for every symbol of x, so it means how many bits you need to encode it. Okay, so that's basically it, right? For example, let's say if you have a source, a Bernoulli source, right? Flip a coin, for example, right? Let's say with probability half, okay, every time. And then you do that for long, okay? And if you want to encode this information, so at most you need 1 bit per symbol. Okay, so that's basically what it means. Okay, so now let's prove it, right? As we mentioned before, so we need to show the achievability and the converse. Achievability basically means that we need to provide a scheme, design scheme, to show this rate is achievable, okay? And for converse, it's an impossibility. So we need to manipulate, some inequalities to show that, this R is upper bounded by this. Okay, so that's basically the idea. Okay, so let's see. Okay, so yeah, we're going to talk about data compression or source coding. Okay, so we're going to prove Shannon's first coding theorem, right? As we said, we need to do 2 things. The first one is achievability. Right here, what we need to show is that R has to be less than or equal to, oh, yeah, converse is a lower bound. Yeah, I always made this mistake. Yeah, so we need to make sure that as long as R is less than or equal to the entropy plus an arbitrarily small epsilon, then we're fine. So we have to build a scheme to show that, right? So that's for all epsilon bigger than 0. And then we can show that, so this guy goes to 0. Okay, so as n goes to infinity. Okay, so this is achievability. And for the converse, so it's the impossibility, right? So basically it means that we need to show that, so when the error goes to 0, R has to be at least this guy. Okay, so that's for all epsilon. And this guy goes to 0 and goes to infinity. Okay, so that's basically our idea. So yeah, let's see how we can show the achievability first, okay? So any idea? Simple idea. Anyone read the book beforehand? Nobody? Okay, if you read the book, probably yeah, you didn't see what I will talk about, right? In the book, it gives you explicit construction of a code showing that so H is more or less okay. Okay, but we want to show you, a very information theoretic thought or Shannon theoretic thought. Okay, let's see how we can do that. So basically, yeah, I kind of mentioned that to some of you before. So we're going to use a property of AEP here. the important thing here is that, so for the achievability, we always use AEP, okay? And for the converse, so we use what? The 4 inequalities that we talk about, more or less, right? Of course, sometimes we use some of the inequality for the achievability as well, but more or less it's like that, okay? Achievability, we use AEP. Converse, we use the 4 important inequality, okay? Let's see how we use AEP. It's almost straightforward, right? So what we're going to do is like this. As we said, right, so this is a set of the total alphabet, right, total source information, okay? And this set is a set of the typical set, okay? So what we're going to do to design scheme is very straightforward. So basically what we're going to do is that for anything here that is not in the typical set, we ignore that. Yeah, we throw that away, okay? And for everything in the typical set, we give a code word. We consider every element in the typical set as a code word. Does that make sense? Right, so basically it means it feels like it's not sourceless, right? Lossless, right? We definitely lose something because we throw out some source information, right? But the thing here is that, so lossless basically means that error will approach to 0, right? It's not exactly 0, right? That is very important mindset. Okay, we want small error, but not exactly 0 error. Okay, that's why this kind of thing can work. Okay, so the coding now becomes very straightforward. So basically, so we need to, follow the definition of the source coding, right? We need to design an encoding function, and then we need to design a decoding function, and then we need to compute the rate, and then we need to show the error will go to 0. Okay, that's what we're going to do. Okay, so the encoding function is very straightforward. So we're going to assign a distinct fx to each x in the typical set. Okay, so this fx would be nothing but just in the indices from 1, 2, up to this. Okay, so that's how I do the encoding. So assign everything in the typical set in this index. Okay, and then we're going to just transmit this index. Okay, and then it is not enough yet because so for the source information is everything here, right? So what about for the rest, right? We throw that away, right? But for the decoder, it needs to know what is going on. So basically, we say when something is here, then we assign a special symbol for it. So it is an error. Okay, so basically we assign this guy equals to an error to all x that is not in the typical set. Okay, therefore the total number of symbols we have is what? Or the total number of indices we have is the cardinality of the typical set plus 1. Okay, so that's the encoding. Okay, for the decoding, so this x hat will equal to g of fx. Okay. Okay, so we say x hat equals to this if there exists, so this symbol means exists, right? There exists a unique x hat that is in this guy. Right, and then we just decode it. Okay, is that clear? So basically, we receive a bunch of indices, right? And then each indices corresponding an element, in the typical set, right? We'll just map it back, right? So if it's in the typical set, right? So if we receive an E there, we say it's just an error. Is that clear? Okay, that's how we do it. All right, okay, so now let's compute the rate. Okay, so now we have encoding function, we have decoding function, and now let's compute the rate. Okay, as we said, rate equals to this. Okay, so now let's compute it. So this equals to log 2, and then inside is the cardinality of a typical set plus 1. Okay, and then we divide it by n. Right? So, okay, so do we know the cardinality of a typical set? Yeah, remember the 4 properties of typical set, right? We have upper bound for the cardinality, right? So here we need upper bound, right? Remember our goal is to show R is less than this number, right? So we need upper bound here. We just apply the upper bound of the typical set. So basically, so this is what we got. Upper bound is 2 power n hx plus epsilon. So hopefully you still remember that. And then we plus 1 here, right? We also have a lower bound, right? Lower bound is 1 minus epsilon and hx minus epsilon, right? That's the lower bound. Here is upper bound. We just need the upper bound here. All right, so now I think it's pretty clear, right? If there's no 1 here, so this will equal to what? Just equal to n hx. So we have a n in front, right? We don't have this n anymore, right? We'll just have this if we don't have this 1, right? Okay, but if it's 1, it doesn't matter. You can work it out. So we can show, this 1 corresponding to a kind of epsilon n prime, right? And this will go to 0 when n goes to infinity. Okay, so yeah, you can check it yourself. Just make these 2 equal, and you can figure out what epsilon prime equal to. Okay, so it will be a very small number. Intuitively, is so this guy would be goes to infinity, right? It's just constant, so it doesn't matter too much. Okay, and we combine this epsilon and epsilon n prime, and then this together is a new epsilon, right? Which satisfies this form, right? And then we're done. Okay, so this is basically the achievability. Okay. Okay. Yeah, and we're not exactly done yet, right? So now we have encoding function, we have decoding function, we compute the rate, and then we need to show the error goes to 0. Okay. So what is the error? Right. So we need to write down what is the formula of the error, right? Error means when something that is not in the typical set, right? So that's equal to the probability that x is not in the typical set, right? And we need the upper bound on that, right? What is the upper bound on that?
1 minus epsilon times 2 to the...
It's just epsilon, right? It's not in the, sorry, my bad. Not in the typical set, right? So that will be less than epsilon, right? Again, the 4 properties, right? So the probability that x in the typical set is bigger than 1 minus epsilon, right? Therefore, this probability will be less than epsilon, okay? Okay, and then we can say that because epsilon is arbitrary, right? So this is a property 2. Okay, and then we can say that, so when n goes to infinity, then this guy will become 0. Okay, and then we're done. Right, that's basically achievability. Right, if you read the book, so it will give you a more concrete construction. So this construction, yeah, just very simple, okay, and give you an idea how to use the typical set. Okay.
So is there a small typo? You say for the error, you say on the assign fx equal to
yeah, not.
For all not, yeah.
Yes. Very good. Yeah, now let's review the procedure here, right? So basically, number 1, we need to design an encoding function. Okay, number 2, we need to design a decoding function, right? And then compute the rate, and then show the error goes to 0. Okay, these are 4 steps. Okay, so step Yeah, let's mark it. Step 1, step 2, step 3, and step 4. Right? So in this example, it's almost trivial, right? It's very straightforward. But later on, we'll talk about something more complicated, so it'll become more involved, right? But you still need to follow these 4 steps. Okay, very good. So any other questions? Okay, so if not, let's show the converse. Or the impossibility. So this is very hard, okay? So converse is one of the most challenging proof in information theory, right? Again, I'm going to show you a very, very simple proof, right? But it's very representative. For all the proof in the future, it follows these steps, okay? Okay, let's see how we can do that, okay? Yeah, I'm now going to ask you, what's your idea, right? So if you have not seen that, so it's very, very hard. Okay, but we just follow that. Okay, so what we do is like this. So NR is a rate, right? Rate multiplied N, right? So this equals to log of the cardinality of I, right? Because, yeah, you can say space 2 or not, it doesn't matter too much, right? Because 2 power of NR equals cardinality of I, right? So is this clear? Okay, so next, very important. So we're going to use, as we said, we're going to use all the 4, most of the 4 important inequalities here, or is, corollary. Okay, the number one thing we're going to use is as this. So this is bigger than or equal to HM, right? So remember what is M, so probably, yeah, let's do it here. So basically, XN is our source information. And then we encode that SN, which is our indices, right, from 1 to the cardinality of I, something like that, right? Or, one more error turn. And then we do the decoding, right? So, okay, this is how we do that. Okay, because, this is the code alphabet, right? So that will be bigger than the entropy of N. So this is the cardinality bound. Okay, so when you read here, you may think, okay, what is the cardinality bound, right? In order to show that, what do we need? How did we show that? Okay, can anyone say it? How can we show this?
Take a divergence with the uniform distribution.
Exactly, very good, right? So basically what we show is that we show a convexity of relative entropy, right? And then, when the Q term in the relative entropy is a uniform distribution, and then we have something minus entropy, right? And then something is basically the cardinality bound, okay? Because the relative entropy is convex, entropy is concave, okay? And we have this, okay? Very good. Okay, great. So basically, every time we will see that, you may think, how did we show this kind of thing? And then it can help you to remember things, okay? So next step is very important. So we always do this. So we're going to use this guy minus this. Okay, see whether that makes sense or not. Okay? And clearly, so why is the equal sign? Because this guy is 0. Right? Because if we know the source, of course, we know M exactly. Right? There's no uncertainty, so this guy's M. Okay? Okay, then what's the benefit of doing this, right? You can see, so does anyone recognize this? So what is that? Very good, the mutual information, right? Mutual information between M and X. Okay, so that is very important. For the converse proof, we always want mutual information. Okay, so this is the way to create mutual information. We always do that. Okay, if we know the mutual information, the next step, I think it will become very obvious, right? Because we did that before. So now we expand mutual information in this way. So now we're going to expand it in another way, right? The other way is that we take this guy first, right? And then minus this, right? Very good. Okay, so now remember our goal, right? Our goal is to show R is bigger than this, right? Let's go back. Remember, we are going to show R is bigger than H minus epsilon. Okay? Right? And we're almost there, right? Because X are IID, right? Because it's IID, so we can take this N out, okay, and cancel the N here. We're almost there, but there's a troublemaker here. We need to make this guy arbitrarily small, right? Remember, our goal is to show our goal. Let's remind you, R is bigger than or equal to this guy. Okay, this guy, right? Okay, and here we're almost there, but we need to make sure this guy is very small. How can we make sure that? So any idea? So basically, we need a bound. We need an upper bound for the conditional entropy. Do we see that kind of thing before? Like all of our 4 important inequality. So is there an inequality to tell us how to bound conditional entropy? Right. First one, Jensen. Right. Second one. What's the second one? Log sum. Right. Third one, data processing. Right. Last one, funnel. Right. What is funnel? Nobody remember funnel? Yeah, that's not good. Yeah, that is very important. I guarantee you that for all of our converse proof, we're going to use that. Right, hopefully, now you recall what is funnel, right? Yeah, let me remind you, right? Yeah, we're going to use a simple version of funnel, right? Funnel basically means this x given x hat, so that will be less than or equal to 1 plus PE log. Let me think. Cardinality of x. Right? Remember that? So we say, okay, we can use that to have a lower bound for our error, right? But so it's the upper bound for the conditional entropy. Remember that? Okay. So now we're going to use funnel, okay? Because funnel is a way to bound it. But can we use that directly? We cannot, right? Because so this is x given x hat. X hat is the estimate of x. But here we have xn given m. It's not x hat. Right? How can we do this? Any idea? But what we do know is this, right? So what is that? From xn to m to x hat n, so this is a Markov chain, right? So if we see a Markov chain, and then we need to find a relation between, something regards to xn m and something regards to xn and x hat n. Does that remind you anything? Yeah, again, think about the 4 inequality, right? Number 1, Jensen. Number 2, log sum. Right? Number 3, data processing. So what is data processing?
It's the one where we said like the entropy from like xn to like x hat has to be
mutual information. Right? The mutual information between this guy and this guy would be bigger or less than the mutual information between this guy and this guy. Right? So yeah, basically that is what we're going to use. Right? So basically what we do is that the mutual information between this and this, so something further away, is less than or equal to mutual information between this and that. Right? Data processing. Okay? Data processing inequality. Right? And then, so we can expand it. Right? So you can expand it in whatever way you want, right? So if one way doesn't work, you just try it the other way, okay? So this is less than or equal to yeah, so Yeah, probably this way is not going to work. Right, so oh yeah, so no, should be x and not x and hat. Okay, yeah, then it works, right? So now we can see that we can cancel this. Okay, and then we can conclude that. So this guy is less than or equal to this guy. Okay, then it means that we have upper bound on this, right? That's what we want, right? So let's see. Okay, so this will become here, right? So basically, that would be bigger than or equal to, right? Right, because we have our upper bound on that, we replace that here, then we have a lower bound. Is that clear? Right. So now we're going to use funnel here, right? So by funnel, right? So this guy will be less than or equal to PE n log the cardinality of this guy, right? Okay, and this equals to 1 plus n p n log this. Okay, and then we can write everything together here because the x are independent. So we can break it into sum, right? We have n times this guy minus 1 minus PE n log x. Okay, so then, yeah, this is nr, right? nr, I mean, I cannot write that, right? So it's a bigger than or equal to, so nr is bigger than or equal to that, and then we can say r is bigger than or equal to this 1 over n minus PE log this. Okay, and clearly as n goes to infinity, so this guy will go to 0, and for PE, so when n goes to infinity, so this guy will go to 0. Okay, so why is that? So we let it, right? Because that's a requirement. Okay, it's in the definition, right? So when n goes to infinity, so error has to go to 0. Otherwise, the code is not feasible. Okay, we let it go to 0. Okay, and then we can conclude that so r is bigger than or equal to h of x minus epsilon prime for any epsilon prime. Okay, so for sufficiently large n. Okay, and then we're done. So this is the converse. Any question? Yes?
But I don't understand how to get from the line 3 to line 4 because.
Which line? I mean from here to here?
Yeah.
From here to here?
The reason that the hm is less equal to h x hat.
Yes, so it's upper bound on that, right? So basically, so this guy has a lower bound, right? Because we replace this guy by this.
But hx height is bigger than h.
Yeah, it's minus here, right? So what we do is that, so this minus that, right? And we have upper bound for this. Right, what we show is that, so this guy is less than or equal to this. Okay, and then, then we have a lower bound, right? So that guy is bigger than or equal to this minus the upper bound.
Okay.
Is that clear? Yeah, so, yeah, here should be bigger than or equal to. Okay, so any other question? Okay, so now let's summarize, right? So let's see what we did for prove the converse. So as we said before, so when we prove a converse, it always follows the steps here, okay? So there are 4 steps. So number 1, so we need to relate, the rate to the entropy of the code word, okay? So that's step 1. Step 2, we need to write everything, in terms of this. So basically, we need to create the mutual information, okay? Step 3 is to expand the mutual information in another way, okay? And step 4 is to use funnel. So funnel is step 4, right? Because once we have this conditional mutual information, by some manipulation, so we can get this, and then by using funnel, and then so this guy will disappear. Okay, so that's the idea all the time. Okay, and in most of the paper you'll see, so they jump from the step 1 to step 4 directly. So basically what they do, now in our proof it's kind of very simple, right? But in reality what they do is that they jump from here to here directly. They just write this 1 step. But what's going on is like 4 steps. Okay, so once you get familiar with that, it'll be like trivial to you. Okay, so that is very important. Any question? Okay, so we need to do the 4 steps, okay? All right, so, okay, still have some time. So let's start another topic here. So now we focus on DMS, right? Discrete memory list source. Okay, so next we're going to see what happens if we have source with memory. Okay, so so let's write down a bunch of definitions, and then we'll discuss some details next lecture. Okay, so so the first thing is that how can we define mathematically define a source with memory? So any idea? Right, for discrete memory list, we assume so every we model that as a sequence of a random variable, or we model that as a random vector. Okay, but for all the elements there, they're IID, right? Independently identically distributed, right? But now, for a source with memory, how can we model that? Right, so basically we use a random process to model it, right? We still assume a sequence of random variables. We assume that follows some random process. Okay, that's how we model that. Yeah, let's write down the definition. So we say a discrete information source with memory over the alphabet X is discrete time random process okay, just use a random process to model this discrete source with memory. So where xi, oh yeah, I didn't write the random process. So we denote the random process as this xi and I in some indices, where xi is a random variable over x. Okay, and here I is the indices set, right? It's 1, 2, 3, and so on, or all the integers. Okay, Z is a set of all the integers. Okay. All right. So given a random process, so basically the first thing we need to think is what are the distribution of this random process, right? So here we model that using the joint distribution, okay? So a random process is characterized by its nth joint PMFs, right? So that denoted as x probability P of x1, x2, up to xn for all n tuples of indices E9, right? And n is from 1, 2, 3, and so on, okay? So I have a random process, and we have its PMF. Okay, so next thing is that, okay, so this is a very general definition, right? And we cannot, study, arbitrary distribution, right? So we're going to focus on a very specific kind of distribution, right? In almost, every area, in applied math related. So for random process, we need to focus on a very specific kind of random process. So it's called stationary random process. Okay, so let's see what is the definition of the stationary random process. So who heard of that before? So who learned that? Great. So what is it?
I think it's the statistics don't change as you
yes. Yeah. What statistic exactly?
The mean, the variance, and the autocovariance or something.
Yeah, that's called White-Sand stationary, right? So yeah, here we focus on more like strict way, but that's very good. So it's it's kind of strict stationary. So basically, what's your name? Norman. Okay, so what Norman said is basically a very weak kind of stationary, right? So basically, only the first moment and second moment doesn't change, right? So what we're talking about is more strict, right? What we're talking about is that the distribution does not change over time. Okay, let's see what we mean by that exactly. So we say a random process, this xi. So we assume I now is kind of like a finite number of elements, right? So this is called stationary. Okay, if for all n and l, so I will tell you what l is. So we have this x1 to xn, right? And then, so the probability that x1 equals to x1, x2 equals to x2, up to xn equals to xn, right? So that equals to if we shift this random process by some time, right? And this amount is L, right? So that equals to x1 plus L equals to x1, x2 plus L equals to x2, up to xn plus L equals to xn, right? You can see that. So when we shift this random process over time, then the distribution is exactly the same, right? And this is a very strong assumption on the stationary. Okay. So that ring any bell, right? Probably you should learn, define this first, and then, for some signal processing class, then they'll give you the idea of the White-Sand stationary. Okay. Okay. So this is the basic definition of stationary, right? So now we're going to again. So even if for this kind of distribution, it is still not very easy to analyze, right? So then we need to focus on a specific kind of random process. Hopefully that is stationary, and it's very easy to analyze, right? So we're going to focus on Markov chain. Okay. So let's discuss some details about Markov chain. So I assume most of you didn't learn that before, right? Who learned Markov chain before in detail? Yeah, only one. Okay. Yeah, that's good, right? So I'll give you the basic concept of Markov chain, right? Yeah, because we're talking about the memory source, right? So Markov chain is very important, okay? And then we're going to just focus on Markov chain in the rest of our class, Okay, so basically, what we think about two kinds of random process most likely. Number one, IID, the other one Markov chain. Okay. Okay, let's define a Markov chain. Yeah, although we have kind of talked about that before, and we talked about definition, right? So let's just refresh it. Okay, so we say a discrete time Markov chain. Yeah, this is very important. We use MC to represent Markov chain. Yeah, this discrete time Markov chain. So this is our favorite. Okay, so it is totally different from continuous time Markov chain. Right? Who learned continuous time Markov chain here? No? Yeah, so that's a total different animal. Okay, so yeah, we don't need to worry about that at all. Yeah, but you know, the extension from discrete time to continuous time is not trivial at all. Okay, you may, yeah, let me write it down, then I will talk a little bit. So it's random process. So this is a random process. Okay, such that the probability that xn equals to xn given all the history of it equals to this, xn minus 2 equals to xn minus 2, and so on, up to x1 equals to x. So this guy will just equals to this xn given equals to xn given xn minus 1 equals to this. Okay, so this is the definition of Markov chain. Okay, so Markov chain doesn't mean it is stationary. Okay, yes?
The first condition is supposed to be x of n minus 1 equals x of n minus 1.
Yeah, definitely. Yeah, very good. So basically, Markov chain basically means that, so the conditional distribution here, or the transition distribution, only depends on the last state, right? And it's independent of the history before that. Okay, yeah. So Markov chain doesn't mean it is stationary, right? And what we care about is a stationary Markov chain, right? But Markov chain itself, it does not guarantee it is stationary, right? And one intuitive thing you can see here is that you can see, so the beauty here is that, so this n represents time. You can, or, you know, it's kind of like time. And when it has a transition, it's at integers, right? A transition from n minus 1 to n, you know, from n to n plus 1, and from whatever, right? So that's why it is very, you know, very nice to analyze. But if it's continuous time, so basically it means that the transition can be arbitrary, right? Because now time is continuous, right? So at any time, it can do the transition, right? Then it will make things extremely complicated. Okay, that's why it's not easy to play with, right? So we focus on the discrete Markov chain. Okay. Okay. So then we can write the implication here, right? So if we just keep doing, you know, this expansion, so we can write down this joint distribution as this guy, right? We kind of seen this before using the Bayesian rule, right? But the general form is that if we take x1 out, right, and then we take x2 out, and then we just keep doing this, so you can see that it is equals to until xn given xn minus 1, right? So it's very nice. We have probability of x1 times probability of x2 given x1, and times probability of x3 given x2, and so on. Okay, so we can write that because we can ignore everything else, you know, in the condition. Okay, so and in addition, we can also say that. We can also say, so this guy, if we consider, you know, group everything else, you know, as one random variable. So yeah, remember, so this basically means the vector, right, from x1 to xi minus 2, right? And this and xi, so that's a single random variable, and xi minus 1, and here's xi. So this also forms a Markov chain. Okay, and based on Markov chain, so we have a new definition. So we say an information source x1, x2, up to xn, and so on. So it's called a Markov source if it forms a Markov chain. Okay, so that's Markov source. Yeah. Yeah, we're going to continue next time. Okay, and that's it for today. Thank you.